All right, so we're going to cover three different environmental considerations: exposure to heat, exposure to altitude, and exposure to cold. And sometimes, by the way, these three things interact as well. And we're not going to cover those interactions too much, but hopefully I'll cover enough of the physiology that you can understand how they might interact. So with heat, we're going to cover heat generation and dissipation, acclimation, hydration, and performance strategies. So first, heat generation. And I'd love you to pull out a piece of paper and do some of this math because it's really good practice for you, and it should pull back some of the aerobic considerations, the aerobic calculations, which is really good review for you, especially because we have exam two coming up next week. So muscular work produces heat, right? About 80% of the caloric expenditure is lost as heat. So you should be able to calculate running 1 mile and how many calories that consumes. So I went to the Google Compendium and I looked up that to run a 12-minute mile, which is anywhere from 5 to 5.2 miles per hour, the Met value is 8.5. Okay, with those two pieces of information, you should be able to calculate how many calories are expended for running that mile. Now, I calculated for someone my size, and for someone my size, it's 134 calories. Now, we know that 80% of that is lost to heat. So 107 calories then are lost as heat. Okay, so that's 80% of 134. And 1 calorie or 1 kcal is literally the definition of it is that it raises 1 kilogram of water 1 degree Celsius. Okay, that's the definition of 1 kcal. Humans, we know, are 50 to 60% water. So then if I take my kilograms, so I'm about 75 kilograms. If I take 75 kilograms and I multiply that by 50%, right, I'm looking at whatever that is, like um, 37 and a half kilograms of me is water. Okay. And if I raise, then that water by 1 degree Celsius, right? If I'm generating 107 kcals of heat, right, that then should raise my body temperature by like 50 degrees Celsius. Okay. And this is how much it should raise my body temperature. My body temperature is already at about 30, what is it, 35 degrees Celsius or 98 degrees Fahrenheit. Okay. So if I increased that by 50 degrees Celsius or 122 degrees Fahrenheit, like I would be dead. 100% would dead. Um, Although that wouldn't last very long because then I would, once I died, like metabolism would stop and I would cool down. But in any case, dead for sure. Um, okay, so, but what actually happens, right? If we look over here on the right, this was 8 elite cyclists and they were doing 60 minutes of work. Okay. And what we saw is, right, their core temperature started at around 37 degrees Celsius. Okay. And it looks like it peaked at around 40 minutes, and its peak was at about 38.7 degrees Celsius. Okay, so it increased 2.5 degrees Celsius, not 50 degrees Celsius. But the math says it should have increased 50 degrees Celsius. Okay, that's if we were a closed system, meaning all of that heat stayed inside of us. Okay, so we know that it doesn't. And there's lots of ways that we lose and gain heat, right? So we gain heat, of course, metabolically, but we also gain heat by radiation. If I was running on turf or even cement, right? However, that solar radiation is reflecting off of the ground and up into my body. We also have ground thermal radiation, right? There we have this hot core at the bottom of the earth. So there is some heat transfer that's happening as a result of that. Okay, so we've got all of those things generating heat. We've also got a lot of ways to lose heat. Okay, so we could lose heat, especially by evaporation, right? So we sweat and that sweat evaporates and that results in heat loss. Okay, we have it by radiation. Okay, so I'm just literally because the ambient air temperature, if the ambient air temperature is cooler than my skin temperature, then I'm going to lose heat by convection and by radiation. And then we also have losses via conduction and respiration. So conduction, right? My muscles are attached or are next to my skin. And if the muscle is hotter than the skin, there's going to be some heat transfer there with conduction. And then respiration, that one's really interesting, but essentially what there's a couple of things that happen. I'm not actually going to go into the physiology, but it's actually really interesting how we lose heat through respiration. It's not the same as evaporation. It's about water changing states. Anyway, really interesting stuff. So if we come down here, the rate of energy production, right, we already calculated is 134 kcals, and we said that that was in 12 minutes, which is 0.2 hours. Okay. So I'm generating heat at a rate of 670 kcals per hour. My metabolic heat rate is I'm generated 107 kcals in that same time frame, so it's 535 kcals per hour. So that's the rate of heat production, and we specify that with Q. So we have Q metabolic, so that's heat production, right? Um, and that is associated with 535 kcals per hour. Okay. Now, we've got a lot of different ways, right, to lose heat that I just went over. So if we take the Q of evaporation, right, we can evaporate anywhere from about a half a liter to sometimes as much as 2 liters per hour of water. Okay. So we just took a rough value running not too intensely, right? And I'm sweating at 0.65 liters per hour. For every liter of water that I evaporate, I lose 580 calories. Okay, 580 calories of heat is lost. So if I evaporated 0.65, I'm going to lose 377 kcals per hour if my sweat rate is 0.65 liters per hour. Okay, and that's just a range there. Okay. Um, then I'm also going to lose some with radiation and convection, right? If we assume that it's a moderately warm day, right? Even if it's 85 degrees outside, ambient air temperature is still cooler than my body temperature, which sits typically at 98.6, but actually we know that, right, with the metabolic heat, that is rising. So we've got a pretty big heat differential. So we're going to lose about 140 kcals per hour due to radiation and convection. And then conduction and respiration, much less, but about 15 kcals per hour, so still some reduction. So if we then combine all of that, right, we have heat generation through metabolic, then we've got heat loss through evaporation, heat loss through radiation and convection, and then heat loss through conduction and respiration. And that's equal to 3 kcals per hour of heat production. So if I balance that, then I'm going to produce 3 kcals extra of heat per hour. And I exercised for 12 minutes. Okay. So I'm going to produce 6 kcals then during that 12-minute run in excess, meaning my body temperature then is going to rise by 0.6 degrees Celsius in that 12 minutes. Okay. So now that looks a lot more reasonable, right? When we come back to the actual data. So I'm going to raise 0.6. That would put me right up about here at 12 minutes. All right. Looks like I'm actually doing better than the cyclists were. Okay. Just by a little bit. Okay. So that just gives you a sense for, okay, right, I've got all of this heat generated. How do I lose that? And through which processes do I lose that heat? And you should be familiar with the process. You don't need to memorize that equation, right? But you should be familiar with different ways that we lose heat and how we're typically producing heat. So now I want you to just spend some time, and I'm not even going to go over this, but I want you then to consider it. So we're generating less heat or dissipating more heat. That's the only way to decrease heat storage. So I want you to consider environmental factors, exercise factors, clothing factors, physiologic factors, both acutely and chronically, and how those might impact generating less heat or dissipating more heat. And I want you, if you see a classmate that has already commented on one of the categories that you thought of immediately, comment on a different category, right? I want to generate some discussion here. So, oh, I actually gave you a perfect prompt. Look at that. So pick 2 categories, explain one factor from each that would affect heat storage. Uh, um, and for each, name which term of heat storage the equation it primarily affects. So that's heat production, evaporation, radiation, convection, conduction, or respiration, and why. And yes, it's me giving you busy work during this slide, but it's also a good way for you to then remember this so that when I ask you to explain the physiology of heat dissipation on your post-class engagement, right, you can tell me. If you do this activity, at least the one that you said, well, you'll probably remember, and maybe one or two that your classmate said as well. Now, also consider how would your choices change in hot or humid conditions and be explicit about, again, which pathway becomes more or less effective and how that might shift your strategy. So I don't want you to pick a new one. I just want you to go off of, okay, the one that I picked, is that going to be affected by a hot or humid environment and how? Like I said, I'm not going to cover that. I want you to just do some thinking. Okay. There's a million different things I could cover, which is partly why I'm not covering it. I want you to generate the ideas there. Okay, so what happens then with acclimation, right? So we can acclimate to a lot of different environments. So this is just a time course of adaptation. So day one, I am now training in a hot environment. And what I see is that plasma volume starts to increase. So literally the amount of water in my blood starts to increase across time. I also see thermal comfort is increasing. So I'm actually just feeling more comfortable. I see sweat rate is increasing, right? It makes sense too that if I have plasma volume increasing, then sweat rate is also going to be able to increase. And then lastly, exercise capacity is going to increase as well. Okay, what's then decreasing? So decreasing is skin temperature, right? So we see skin temperature decrease pretty quick in the first couple of days. We see core temperature also decreasing, actually more so even than skin temperature. And then we see heart rate decreasing drastically across this 7-day acclimation period. Okay. So we see that acclimation happens anywhere between about 7 to 14 days. You can see that most of the adaptations happen before 7 days. Now it looks like, right, we might have sweat rate is still increasing at that point. But most adaptation is achieved by about 7 days in. This is some really cool research showing that you can artificially help someone acclimate. So this figure in the bottom left, this was using sauna. So they had people sit in a sauna and they said, okay, does your plasma volume change just as a result of sitting in a sauna? And in fact, yes, it does. We see that on average, participants increase plasma volume by about 10% just as a result of sauna exposure, right? And plasma volume here, we saw if it started at 100%, it increased up to, again, about 10 to 15%. Okay. So you can actually see really similar adaptation just with sauna exposure. On the right-hand side, they were using a hot tub actually uh, as the exposure in this case, and it led to increased sweating at a lower skin and rectal core temperature. So the rate at which sweating starts actually changes. And you can see that like in those running in a cool environment versus a hot environment, right? The hot environment time to completion, this is a performance measure, increases, right? Which we would think, okay? But it is significantly lower in the group who was engaging in hot tub. Okay. Um, I use this upper plot just to show you. So the individual lines are what we call a spaghetti plot, meaning they plot individual responses and the bars plot group responses. But sometimes it's really helpful to see this because we often think, oh, well, that works for everybody. If we look here, especially, right, the this particular individual actually, and this was temperature, skin temperature, they actually saw a significant increase, right, in skin temperature, whereas this person saw a significant decrease in skin temperature. Okay, so they had completely different responses as a result of the same exposure. And you can see that some here, right? That's increased, that's decreased, right? Even though the average of the group might be different. So anyway, it's just sometimes helpful for you to understand individual responses are different from group responses. So this was actual acclimation. Okay, so they actually exposed them to oh no, this was pre-acclimation. I don't remember what the I think this must have been sauna exposure. I thought it was just exposure to, I think it's just exposure to the heat though, actually. So I think it was environmental exposure in this case. And they looked at a bunch of different outcomes, but acclimation, I summarized it here for you. Acclimation resulted in greater stroke volume, greater cardiac output, greater functional threshold power. It's essentially the work at lactate threshold that you can perform. Um, increased VO2 max, and improved time trial performance with acclimation, right? So if we acclimate, whether artificially or with exposure to the environment, we can see a lot of improvements in physiologic markers as well as improvements in performance. Okay, so this is a good case study to run you through, again, just to give you some practice. For the record, I don't expect you to memorize that equation. I'm just giving you some practice using it so that you do remember the concepts that the equation represents. I will never actually ask you to calculate this, but it's a really good thought experiment. So I'm giving you the equation, right? So heat storage, metabolic heat production, evaporation, radiation, conduction, or no, this is convection. Um, this is conduction and respiratory, okay? And it's in kcals per hour. So metabolic heat production, evaporation, radiation, conduction, and respiratory. Okay, and what I want you to do is compute S and state whether the core temperature is rising, stable, or falling. Okay, that's your first task. Then you hand this athlete, a cooling towel and increase fan airflow, raising E by plus 60 and R plus C by plus 20. Now recalculate, and are we rising in temperature, stable, or falling? Okay, so right, this was an intervention. And how was the intervention? How effective was the intervention? Then in one sentence, match each of these strategies to the term they primarily improve above. So if you remove a layer of clothing, right, am I associating that with which one of these? Okay. If I add a cold, wet forearm towel, which one of these? If I move into the shade with a breeze, which one of these is most affected? If the humidity increases suddenly, which term then is most affected and what happens to S? Okay, again, answer these on perusal because it's good practice for you, not because I'm going to have you calculate this at some point. The answers, by the way, to this particular one, if you download the PowerPoint, they're in the slide notes for you. Hydration recommendations. This is where I need you to pay very close attention because I do expect you to memorize and know these. Okay, so pre-exercise, the recommendation, and some of these come from the book, some of these come from literature. Okay, this one is from the book. So 4 hours before exercise, the recommendation is to drink 0.1 ounces per pound of body weight. Okay. If you do not urinate, or if your urine is dark 2 hours before engaging in exercise, you're going to drink again half that amount, so 0.05 ounces per pound of body weight. During that time, also, you may add 1 to 3 milligrams per kilogram of caffeine. Ideally, that's taken in about 30 minutes prior to exercise. Okay. Now, and you need to know all of that, by the way. During exercise, this is the Galpin equation. Andy Galpin is a performance scientist. He's he has a PhD in exercise physiology. He came up with this equation. So he encourages drinking your body weight in pounds divided by 30 every 20 minutes. And that's in ounces, okay? You do need to know that 1 liter is equal to 33.8 ounces, okay? Mostly you need to know that because of what comes next. So the recommended amounts of sodium, potassium are based on liters, okay? So 20 to 30 molar equivalents per liter of fluid. Now, what that means for sodium is 460 to 690 milligrams of sodium per liter of fluid, okay? 78 to 195 milligrams of potassium per liter of fluid. And then the carb recommendation is different. And again, you need to know this. So 0.5 grams of carbs per pound of body weight and half that amount of protein. And that's every 60 to 90 minutes. Okay. Then post-exercise, for rehydration, it's 17 ounces per pound of weight loss. So you are just replacing weight loss, right? I didn't lose tissue in a 2-hour event. I did lose a lot of water. So we assume all weight loss comes from fluid loss. Okay. So we're just trying to replace that. If you have another event later in the day and you need to rehydrate more quickly, 23 ounces per pound of weight loss may speed up recovery. And we would still want this same amount, the same composition of fluid. We don't necessarily need this composition of fluid pre-exercise. Okay. This is Gatorade, by the way. So this is just a nutrition facts label. And you're looking at 12 fluid ounces, right? we now know that 33.8 ounces of is a liter. So this is about 30 ounces. So we're just going to assume we're at about a liter. So if I come down here and I look at the sodium, 440, tiny bit low, but pretty close to recommended values. Total carbohydrate, 58 grams, right? That would depend on my body weight. For someone my size, that's a little bit high. I think when I calculated this, I think it was something like recommended value is something like 45 grams, so a little bit high on the carbohydrate. No protein included. And then for potassium, 120 milligrams, right? So sort of right within that range. Okay, so Gatorade does research, and they actually typically are producing beverages based on research. Okay, this slide, really important. You do need to know it. Coming here now, I just wanted to show you some data, and this was from Gatorade as well. So generally, when we say someone's dehydrated, we consider that 2 to 5% of their body mass was lost to fluid reduction, okay? And that does result in an increased heart rate and an increased core temperature. So what they did is they were measuring rectal temperature with 4 different types of ingestion. So this is water plus carbohydrate, just water, just carbohydrate, and then a placebo. So no fluid, no carbohydrate. And right, what we see is that rectal temperature increased the most actually in the carbohydrate group, right? Because they're getting no fluid, and actually to process carbohydrate requires fluid. So that makes sense. Then we have the placebo group, and then there was no statistical significant difference between the water group and the water plus carbohydrate group. Though, right, it does look like the water group itself maybe outperformed the water plus carbohydrate group here. For maximal power, right? So now we want to see if maximal power decreases, we want to maintain that. So we see that the group that maintained the best was water plus carbohydrate. So it may be the intensity of activity, right, is more important for carbohydrate than just core body temperature. So again, there's some nuance when we actually look at the literature. Water was still effective, but not as effective as water plus carbohydrate. And then both the carbohydrate and the placebo group had the greatest reduction in power. Okay. And then there's just some specific data down here, but essentially, right, what we see is with large fluid losses, we see greater reduction in power and greater increases in rectal temperature. So a couple of strategies that you can use to mitigate this is, right, we want to hydrate, we want to acclimatize, and we want to cool. This was in this study, they tested 4 different groups. So they tested unacclimated individuals who were dehydrated or hypohydrated, unacclimated who were euhydrated, and then acclimated euhydrated. And core temperature changes, right? So everyone who's engaging in exercise, right, should see an increase in core temperature, but this group who was acclimated and hydrated was most able to maintain or to reduce increases in core temperature. Okay, and then it looks like, right, that euhydrated status really is important because the euhydrated group was much lower core temperature than the hypohydrated group, both in the unacclimated and the acclimated individuals. Okay, so that hydration status, super important. This is just a forest plot. You see these a lot in epi, okay, but looking at whether or not cooling strategies, so different cooling strategies like a cooling vest, cool water immersion, an ice slurry, cooling packs, or mixed methods of cooling resulted in improvements in ability to maintain core temperature. And what they found was that indeed it did improve ability to maintain core temperature, generally speaking. Okay. This is just more data on that. So looking at cool water ingestion, ice vests, and cooling packs. And again, we saw that they were able to improve temperature regulation. Okay, so case study. Again, this one I would for sure do. I promise this comes up on exam 2, and I think it comes up on your final exam as well. So Sunil is 58 kilograms doing a 2.5-hour steady run in 30 degrees Celsius. After a similar session last week, Sunil's body mass was 1.2 kgs lower at the finish. So your job is to calculate pre-exercise fluid hydration and caffeine consumption, how many ounces, and if urine is still dark at 2 hours, how many additional ounces. Then I want you to calculate during exercise hydration. So what's the total during exercise volume. And then for Sam's per 20-minute drink volume, calculate his sodium, potassium, carbs, and protein. This should take you a little while, right? But I need you to practice it so that on the exam, it takes you less time. So again, answers are in the slide notes for you. So download the PowerPoint, check out the slide notes. And then to calculate post-exercise hydration, how many ounces to rehydrate rapidly. Okay, take some time. Also, just share your answers. If you don't go look at the side notes, maybe share your answers in the perusal so that your classmates don't have to go find it. Okay, heat index. So this is a wet bulb globe temperature. I ask a question about this, I promise, on temperature and relative humidity. So we know that humidity plays a large role in heat risk. Okay, so right, the hotter it is, the more at risk I am. However, if it's really low humidity, my risk is much lower. So even at 100 degrees, if it's really low humidity, risk is much lower. The higher the humidity, the greater the risk. Okay, and that chart corresponds with this chart. So this is your heat risk category. And note that it breaks people up into unacclimated and acclimated individuals. So if my risk is high, okay, and I'm engaging in light work, actually, if I'm acclimated, I can do continuous light work, okay? For moderate work, now I need 30 minutes of work and 30 minutes of rest. If I'm unacclimated, 10 minutes of work, 50 minutes of rest. And if I'm engaging in heavy work, I should avoid doing that if I'm unacclimated and the wet bulb globe temperature reading says that my risk is high, okay? So that's how you would use this. So if I said it's a 100-degree day, humidity is 15%, okay, then my risk is high. So if I wanted to engage in heavy work, I wanted to do some HIIT training, for example, if I'm unacclimated, right, if I haven't spent at least 2 weeks in that hot environment, I should not be then doing heavy work, okay? If I am acclimated, all right, now I can do a little bit, but no more than 20 minutes. And for every 20 minutes I work, I should get 40 minutes of rest. So you can see how that should significantly impact the prescription of exercise, okay? One way that we often see is like at the beginning of a football season in particular, coaches really want to jump into really heavy training really quickly, but the football season often starts in the summer, right? So it's really hot out, and they're not taking into account that wet bulb globe temperature, nor the fact that many of their athletes are probably unacclimated, okay? And that often are not taking into account water intake as well and appropriate levels of water intake, okay? So we see a lot of heat illness then in summer sport. Okay. Your book goes over this, so I'm just going to be really brief here, but cramps, right, is one. We can see muscle spasms there, slightly increased core temperature, but not huge increases typically. Syncope is a brief fainting. You see typically decreases in heart rate, decreases in respiratory rate, pale skin, not necessarily an increase in core body temperature though. For heat exhaustion, we see decreased blood pressure, increased heart rate here, increased respiratory rate, pale skin, and increased temperature. Now, I will say, right, we could have syncope and heat exhaustion occurring at the same time, okay? So I might see elevated heart rate, but at some point, I also might see that drop drastically, and I might have someone fainting. So I could have both of these at the same time, even though it looks like decreased heart rate, increased heart rate, right? Definitely some increase in core body temperature as well, up to about 104 degrees Fahrenheit. Heat stroke is the one where we're really going to be concerned, right? Risk of death is higher here, but I'm going to see disorientation, some irrational behavior, hyperventilation, and significantly increased core temperatures up to about 100 or above 104 degrees Fahrenheit. I promise there are questions on that on your post-class engagement and on exam 2. So heat summary, muscular actions produce heat. Most of that heat is dissipated through evaporation, radiation, and convection. Acclimation improves performance. Timelines differ but plateau at about 2 weeks of exposure, really most of which is happening within the first 7 days, with the exception of sweat rate. Sauna and hot tub can facilitate adaptation. We minimize the effects of heat by focusing on that wet bulb globe temperature. You need to know risk and how that changes prescription. You don't need to know those charts, by the way. You just need to know that that's a tool that you would use to monitor risk. Okay. To minimize the effects, though, appropriate hydration and cooling strategies can be used. All right. I'm going to jump off and then we'll come in and I'll do altitude and cold exposure together.